Isotopes are different versions of the same element. It's basically when an element has the same amount of protons but a different amount of neutrons, which changes its atomic mass.
So now let's move on to radioactivity. An element can be considered radioactive if its nucleus is unstable, thus releasing radiation.
Radiation energy can be emitted in the form of light, heat, or alternatively. Additionally, any element with an atomic number greater than 83 is always radioactive.
Let's head over to the RAP station.
Yo, radioactivity, I'm here to play. I'm U235, but I'm not gonna stay. Cause I'm unstable, but I'm young and I'm able. Besides, I'm more than 83 on the P table. First comes Alpha, helium-4 over 2. Shining center stage, it just made its debut. Now that I'm element 231, you may think that I'm done, but really, I've just begun. Cause I'm thorium, I'm ready to bury my scheme of rhymes. I drop dimes before I transition yet again. I'm going full on beta. This is for all the haters who don't know how to rap as well as me and Darth Vader. Neutron turn into a proton, collect 'em, perfect 'em. Like the fire we spitted, though my mass stays the same. My efforts weren't in vain, as by one my atomic number gains. Yeah, we emit some electrons, but we collect some too. With 35 neutrons, let's head over to CU. Their atomic number decreases. We combine the pieces to form a rap worthy of our Savior Jesus. And boom, just like that, I turn 2 into 1. The electron's done. Sorry about the pun. I hit it with the proton to turn it all anew into a neutron like I'm Newton. Now that it's through, boom, uranium-235 out.
Welcome to our AP Chemistry video about nuclear chemistry made by Aris, Caleb, Avik, and Adam. The first thing we're going to talk about are the different kinds of radiation, starting with alpha.
In alpha radiation, helium-4 particles are created as a product.
Alpha radiation is the weakest kind of radiation, and thus something as thin as a piece of paper can stop its energy.
Here is a perfect example of alpha radiation. There's a uranium-235 atom emitting an alpha particle, that's the helium-4 and turning into thorium-231.
In alpha radiation, the atomic mass of the original atom decreases by 4, and its atomic number decreases by 2.
This shows the nucleus emitting a helium-4 particle. Next up is beta radiation.
Beta radiation involves an emission of an electron, and it's the second weakest type of radiation. Something as weak as a marker can stop it.
In the beta radiation process, a neutron turns into a proton and an electron.
When the neutron breaks down within the nucleus, the proton stays in the nucleus while the beta particle leaves the nucleus.
The mass of the initial atom stays the same, while the atomic number goes up by 1.
The next type of radiation is gamma radiation, which releases pure energy and is the strongest type of radiation. If you're around it, you're probably screwed. Enough said.
Now we are going to focus on positron emission. But what is a positron? A positron is essentially a positively charged electron. In this case, a proton breaks down into a positron and a neutron. This leads to the mass number staying the same, whereas the atomic number decreases by 1.
Electron capture is when an electron gets so close to the nucleus that it gets pulled in and then mixes with another proton to form a neutron. Mass number stays the same, and the atomic number goes down by 1.
The belt of stability is a graph in which the stable isotopes on the periodic table are shown number of neutrons by number of protons. It shows how certain isotopes need to go through certain radiation to become stable. You also may notice that we graphed y equals x on this. This is because the number of neutrons should be greater than the number of protons in a stable isotope. Within the belt is of course not radioactive, but below the belt is either positron emission or electron capture, and left or above, beta, or to the right is alpha radiation. Half-life is the time it takes for half of a given amount of a given material to decay. Here's the equation, which is based on amount and time. NT is the amount at time t, and naught is the initial amount. T is time, and T half is half-life. Thank you for watching this episode based on nuclear chemistry.